So Tobias introduced O-minimality, and many of the properties he talked about make O-minimal structures a good setting for analysis because they rule out a lot of the kind of pathological behavior. For example, he mentioned how definable sets having a good notion of dimension means that we never have to deal with space-filling curves. He also mentioned some O-minimal structures. Rn, Rx, and Rnx. So these are expansions of the real field by real analytic functions. But of course, we can also talk about complex functions of complex numbers in O-minimal structures by identifying the complex plane with R squared. So I'll say that I move the board with this, right? So a function, okay, it's okay. I can use my hand? Oh, okay. So a function from some domain in the complex numbers to C, so U, this is, let's say in C to the n. I want to say that this is definable. Always for me in an O-minimal structure. If the set U viewed as a subset of R to the 2n is definable. And if the real part of f and the imaginary part of f, also as functions of 2m variables, are definable functions. So here I'm using rectangular coordinates, but we can also talk about, make a version of definability for a complex function using polar coordinates. And that will give the same notion as long as you can definably change coordinates. So like as long as restricted sign and cosine are definable. Now, in Rx, the real exponential function is definable. And real analytic functions, they always have a holomorphic continuation to some domain. And the real exponential function extends to the whole, or has an analytic continuation to the whole complex plane. But it's not so obvious that in Rx, whether the analytic continuation of the real exponential function is definable. So in Rx, we can ask, is the complex exponential function definable on some, let's say, open set U? So definitely, the complex exponential function can't be defined on the whole complex plane because it's periodic. So you could define, say, like the set of z such that exp of z equals 1. And that's infinitely many discrete points. So that can't be definable in an O-minimal structure. But in fact, there's no such U on which the complex exponential function, there's no open U on which the complex exponential function is definable. And we can see that with a result of Bianconi. So Bianconi showed that the real sine function is not definable on any open interval in Rx. And then since complex exponentiation can be written as e to the x times cosine y plus I sine y. Of course, we can't define the complex exponential function on any open set in C either, because then we would get the real sine function on an open interval. OK, so there are O-minimal structures with real analytic functions that don't have a definable holomorphic continuation anywhere. But of course, in the case of the sine function, if we look at the real numbers with the real exponential function and the sine function restricted to 0 to 2 pi, this is O-minimal because, for example, it's a reduct of Rnx. And the complex exponential function is it's definable on the set of Z with imaginary part bounded between 0 and 2 pi by the same formula. And from sine, you can identify cosine. You can define cosine. OK, so here we have a couple examples using the real exponential function. Oh, I didn't mean to. It's OK. But we can also ask a general question. So given an O-minimal structure, which definable real analytic functions have definable holomorphic continuations. So in addressing this question, the example with the exponential function is not so useful because, well, we can define a holomorphic continuation of x in the structure with x and restricted sign. But that uses a specific property of exponentiation. It doesn't really say anything about what would happen in the general case. But there is some known. There are some things known. But I guess first let me just say one word about why this question is interesting. So, well, I think it's a natural model theoretic question to ask about definability. But answering it for specific O-minimal structures of interest is also, it's useful. That's because if we know that definable functions in some O-minimal structures actually have definable holomorphic continuations, then we don't only have like the tameness that we get from O-minimality, but we can also use like results from complex analysis, which is better behaved than real analysis. So that's like an extra level of tameness on top of what we get from O-minimality. And there's a whole theory of O-minimal complex analysis. That was developed by Peter Zill and Starchenko. And so this has been used to prove results in Diophantine geometry, functional transcendence. So it's useful to know that definable real analytic functions are actually definable on some portion of the complex plane. So now let me say a little bit about some answers to this question that are known. So first, for Rn, definable real analytic functions in Rn have definable holomorphic continuations. This is a result of Tobias. And then in Rnx, things are more complicated, but it is known that definable unary real analytic functions have definable holomorphic continuations. So this was partially proved by Wilkie, who then used the partial results to prove a definable version of Polya's theorem, which says that integer-valued complex analytic functions are of a specific form. And then the full result for unary functions was again proved by Kaiser and then extended by Tobias and Patrick to functions that are analytic on the Riemann surface for the logarithm. Okay. But there are interesting functions that are not definable in either of these two O-minimal structures, but that are definable in other O-minimal structures. So maybe let me go over here. So this is an O-minimal structure denoted like this. It's called the real field with convergent generalized power series. So we take the real field, and then we also add new functions coming from this collection and star, which I'll say more precisely what that is in a couple minutes. This is proven to be an O-minimal structure by Van den Dries and Speissegger. And also the Riemann zeta function restricted to the interval from 1 to infinity. This is definable in Rn star along with the real exponential function. And this is also O-minimal. Another interesting O-minimal structure is OG, or RG. This is called the real field with multiple multi-summable series. And this, again, is built by adding a lot of new function symbols. And again, I'll say a little bit about what those two are in just a second. But this is also an O-minimal structure. Which again was proved by Van den Dries and Speissegger. And the gamma function, restricted to the positive real numbers, is definable in Rg along with the exponential function, which is also O-minimal. And both the zeta function on this interval and the gamma function on the positive real numbers, those are not definable in Rn x. Okay, so N star and G, these are algebras of functions, or collections of algebras of functions. They both extend the restricted analytic functions. And also, so the functions in N star and G, they come from holomorphic functions that are defined on sector-like domains. They have certain properties, these holomorphic functions, and then they're restricted to unit boxes in the real numbers. So let me say maybe just in one variable what this means. So in one variable, f being in this collection N star or in G that there's a series f, I'm just saying in one variable, either a generalized power series or a multi-summable series. And this has some conditions for convergence. So there's a series f, and f converges on a sector S to a function f tilde. So, okay. Here's the sector S. F tilde this is holomorphic everywhere on the sector except possibly at 0, where it's just C infinity. And then we get F from F tilde by restricting to the interval from 0 to 1. Okay. So the results that with Patrick that I'm going to talk about now, we show for these two structures, Rn star and Rg, that if you take functions in these classes, in n star or in G, then those come from some holomorphic extension, some holomorphic function in a larger region that's then restricted to just the unit interval or unit box, and that's what goes into n star and G. So we know that functions in here do have holomorphic continuations to specific regions that we understand. And so what Patrick and I prove is that this f tilde, it's not only definable when in Rn star or in Rg, when it's restricted to the unit box, but it's actually definable on a large piece of these original sectors. So now let me state the theorem. Yeah.
When you say convergence, do you mean something more or just a
There's specific conditions. I'm just not talking about them.
Something more than just a expansion of sector, for example, for summable series, some additional conditions.
Yes, there's like a very precise thing that, yeah. It's a little bit technical, so I'm not describing them explicitly.
And when you say a series, you mean a power series?
I mean a generalized power series or a multi-summable series. And these are things that they satisfy certain conditions, and they're set up in a particular way to ensure that convergence gives us holomorphic functions on disks like this.
Maybe you should say what you mean by a generalized power series.
Okay. Yeah, okay, so a generalized power series, yeah, the multi-summable series are a little bit hard to actually say what they are, but generalized power series, those are a little bit easier to talk about. So in one variable, a generalized power series, well, a power series is, we all know what power series are. The exponents of the series variable are natural numbers, but in a generalized power series, the exponents are allowed to be sequences of real numbers as long, okay, this is a little bit, but as long as they go to infinity, or as long as they're well ordered.
Do they go to infinity or just
they're well ordered, yeah. Yes, that's the precise thing. They're well ordered. Mm-hmm.
Do you know accumulation points in the support?
Yes. Yes. But for the zeta function, which is what I'm going to talk about, there are no other accumulation points. You just, yeah, there.
And I guess that when you say converges, for the case of multisomable, it's not convergent. There is a Borel Laplace summation that gives you the F tilde, I suppose. I guess. It's not convergent.
It's
series or multisomable are not convergent.
At 0. I mean, yeah.
But we have some time to cut down physical line sectors.
Exactly, yes, this is exactly it, yes. Okay. Okay, I'll just do this one. So let F, the first theorem is for these generalized power series, and then I'll say a second theorem for multi-summable series. And I'm going to state these theorems just in one variable, but they actually hold in any number of variables. So our theorems are for all functions in N star and all functions in G, which are, these are the algebras that we get. There's like one algebra for each number of variables. So our theorems are for the whole classes, but I'm just going to state them in one variable. Okay. So let f of x be a generalized power series. And I'm going to say it has radius of convergence R. And the picture, so here's R and minus R. And so f gives a function that's holomorphic everywhere except the negative real line on this disk. And it's 0. Now for any angle in the interval from 0 to pi, we can draw the sector where this angle here is rho. So I'm talking about this here. Also here. And call this S. So for any row, so any sector like this, the f tilde that we get, so the function that's defined initially on this whole this whole almost disk, except for the minus real line, restricted to S, is definable in Rn star. So this is our first theorem. And now let F be a multi-summable series. And again, I'm going to say that that defines a function f tilde on a sector. Now we can't go all the way to the minus real axis. You know, maybe it's just some sector that looks like this somewhere, and it stops somewhere between 2 pi or pi over 2 and pi. So let's call this S. So this is S. And let rho be an angle between 0, and now this is different from the first theorem. Let's call this angle here phi, the angle of opening of our sector. And I'm going to let rho be an angle from between 0 and phi minus pi over 2. Then f tilde restricted to, let me write the phi here, the sector of opening angle opening rho. So if this is, I have to be less than phi minus pi over 2. So that's like here. So this angle here is rho. And f tilde is definable on this sector. Let me call this S prime. Okay. So of course these are different. Here we have this restriction on how much of the original sector where f tilde is holomorphic that we actually get definability on, and this is optimal. In general, this is the best that can be done, and I'll mention an example later about why.
Excuse me, what was phi?
Phi is this angle here. So we have this sector, and the angle of the half angle of opening is phi. Maybe it's easier if I draw it down here. So this angle here is phi.
It's given by the series.
It's given by the series, yes. So f, yeah, it comes with a phi or maybe a range of phis, such that it gives rise to this holomorphic function on this sector. Mm-hmm.
But it can be less than pi over 2.
We don't allow that because there's this important quasi-analyticity condition. But yeah, I won't talk about that really. So yes, so phi is always, we need it to always be between, or we restrict ourselves to only allow functions in G that come from series F, where the angle that we get is between pi over 2 and pi. Yeah. Yeah, right. So right. There's also an associated radius R.
This radius, is it allowed to be infinity?
No, it's finite. Okay, so these are our theorems. And now, I mentioned over here that it was already known that in these two structures, Rn star along with exp, and then Rg star along with exp, the zeta function on the positive real number is greater than 1, and the gamma function on the positive real numbers, those are definable. So now let me say what these two theorems tell us about the definability of holomorphic continuations of the gamma function and the zeta function in Rn star exp and Rg exp. So first, maybe let me remind you a little bit about the Riemann zeta function. So the zeta function is originally defined as, or it's first defined as a Dirichlet series. And this series converges when the real part of z is bigger than 1. Okay, and it converges to a holomorphic function, zeta, which then has a holomorphic continuation to the rest of the complex plane except z equals 1, where it has a simple pole. And now zeta composed with minus log z this can be expressed as a generalized power series that has radius of convergence 1 over e. And maybe I'll do the calculation because there's time and it's not hard. So if we restrict, let me first say, so if we restrict to the disk of radius 1 over e, and also z is not negative, and okay, just for what I'm going to write, I should write this, I guess. Zeta of minus log z. Well, minus log z will then have real part greater than 1. So we can use the Dirichlet series definition. And now we have a negative exponent here. So we can write this like this. And now we can rewrite n to the log z as e to the log n times log z. And then move z back down. And now this is exactly a generalized power series because these exponents are well ordered when n varies in the natural numbers. Okay. So then theorem 1 gives us that that this is definable on any sector like this, where this angle can be anywhere between 0 and pi. Here. And then if we think about how do you get zeta from this, well, we should compose with e to the minus z. And if you think about how this domain is transformed by doing that, what we get is a region like this. It goes infinitely far off to the right, where let me give this angle a name. Let's say this is rho. And so then here is rho. Here is minus rho. So then this is the region where zeta of z is definable in R and star x. And actually what my collaborator and I do, instead of working just in the complex plane, we work on the Riemann surface for the logarithm. And that allows us to extend the angles further. So we can make this domain of definability as wide as we want. And this is optimal in this structure, at least in this right half plane here, because we can also show that the zeta function in this structure is not definable on any set in this right half plane with unbounded imaginary parts. So this is the best that can be done in R and star exp. And now maybe I'll rearrange the boards and talk about the gamma function. I work in Austria now, so I've learned to use these things, but I'm still used to the eraser. Okay. So the gamma function extends the factorial function on natural numbers to the complex plane minus the non-positive integers. So it satisfies a difference equation. Gamma of z plus 1 is equal to z times gamma of z. And also gamma of 1 is equal to 1. And so from that you can see that gamma of n plus 1 is n factorial. What's important for us is actually a different property of the gamma function. So it can be written in terms of the exponential function, log and this sort of remainder function, phi, on the complex numbers minus the non-positive reals. And so this is due to Stirling. And this remainder term here, it has small modulus away from the minus real numbers. This is sometimes called Stirling series. And I'm talking about Stirling series because if you compose with 1 over z, you can write this as a multi-summable series. Maybe I'll draw the picture over here. It didn't really. So our theorem this multi-summable series, it originally gives a function that's defined, maybe I can make this even better, defined in a sector where the angle gets as close as you want it to get to pi, but we can't go all the way there. So then our theorem says we have to take this angle, subtract pi over 2, and do something a little less than that. And then what you get, if you can get as close as you want here to angle pi, you can get as close as you want here to pi over 2. So we get definability on a sector that's almost a half circle. But not quite. And so that means that phi is definable on any sector that's strictly contained in the right half plane. So yeah, all of this. And then the picture for where this gives us that the gamma function is definable is a little more difficult to draw than that one up there for the zeta function. So now I'll display some images. But I guess I should move this down. Okay, but maybe first I'll say, so Stirling series, or this function, This is definable in any sector strictly contained in the right half plane. So then for the gamma function to be definable, we need to know that this is definable. And we also need to know that this exponent has bounded imaginary parts, because the exponential function is periodic, and we need to make sure that we don't get infinitely much oscillation from the exponential function. So what I'm going to show you pictures of now are the regions where this exponent is bounded between certain values. Do I need to, password. Oh, sorry, thank you. Where's the? So this is what's called a domain coloring. The regions that are dark represent points where gamma of z has small modulus. The regions that are light are points where gamma of z has large modulus. The colors represent the argument of gamma of z. So red represents argument 0. It's a little bit easier to see if I use this other representation of the modulus. So now the modulus is represented by these level curves, but it's easier to see the colors. So what was already known is that the gamma function was definable on the positive real line here. And what our result gives is that it's definable, well, the Stirling function is definable in these sectors in the right half plane. And then the region where this exponent is bounded between, say, or has imaginary part bounded between 0 and 2 pi are exactly, so this curve here, if you follow the red color, and so that's where the argument is 0. This curve here, again following the red color, is where the argument is, where the imaginary part of the exponent is 2 pi. This part is where the imaginary part of the exponent is 4 pi, 8 pi, so on. So 6 pi, 8 pi, yeah. So the region where we get that the gamma function is definable is this rainbow strip, but restricted to the right half plane. But actually, we can take unions of any finitely many of these rainbow strips. But again, we have to restrict them to the right half plane. And so this is again optimal for the structure RGX. We prove that the gamma function is not, and so also the Stirling function is not definable on any unbounded set in the left half plane. And so that's where I will stop.